Shani sir, shall I start?
Yes, sir.
Okay, thank you so much. So, good evening, one and all. So, I think we'll start the session without any formal introductions. So, actually, it's the third or fourth day of FDP, and you all are waiting for different algorithms you are going to learn, you're going to see. So, today we are going to learn, we are going to see one of the traditional algorithm in AI. So before that, if you can see my screen and you can hear my voice very clearly, just type yes in the chat box. Just type yes in the chat box so that I can know you people can hear me. Okay. So I think it's clear. Okay. Okay. So today we are introducing support vector machine. So that is also known as SVM. It's a powerful supervised machine learning algorithm mainly used for classification, regression, then outlier detections. Most commonly, SVM is used for classification problems. Basically, yesterday we have done some spam, non-spam emails. So that you can use in SVM also. Then cancer, non-cancer detections, fake versus real image detections. And most of the type of classification you can do using SVM. So, but we have a gateway through it, like the data must be linearly separable. So if you can separate a data which is very easy to separate, that is especially linearly separable data, you can use SVM. So suppose if you have two groups like class A and class B or any of the classes. So you can think if it is very easy to separate using a line means you can use SVM. So that actually you have to visualize the data while you are performing. So once you visualize the data using some graphs, matplotlib or something like that, you can use the SVM. So first I will check how this SVM is mainly working. So actually you have to find out some hyperplane. Hyperplane means it can be a line. So in two-dimensional, for a two-dimensional data, actually you need a line to separate. For a three-dimensional data, you need a plane. So you can see this is a one-dimensional data, the first graph. To separate this, actually you need a line, but this is not an ideal case to separate. So just think if it is a linearly separable data. So using a line, you can separate, right? So what if it is a three-dimensional data? You need a two-dimensional plane to separate it. So for n-dimensional data for separation, you need n-1 hyperplane. So hyperplane can be a line or a plane or anything. So unfortunately, we are human beings. We can access only three-dimensional view in our mind. So the things are not only three-dimensional, right? It is n-dimensional. So wherever you can separate it linearly, you can use the kernel. But what if it is non-linear? You can't separate it in a single dimension or multi-dimension. You can raise the dimension into different dimension. Either if you can see the data here, once you check in two dimension, you can't separate it. But when you transform it to a different dimension, you can separate it. So these are something which you need to know while you access with the data. So actually, optimal separation. So whether the data is 2D or something like 3D, you need to get a separable data, linearly separable you need to get. So whether if it is 2D, you can separate with a line. Whether if it is a three-dimensional data, you can separate it with what is a plane. So whatever it is, it should be a hyperplane where you can separate it. So first, when you get a data set, when you get a public data set, you have to visualize those data sets and see whether you are able to separate it or not. Okay. And how to draw a hyperplane or how to find out an equation of a plane, I hope you know. So for a line, it is y equal to mx plus c. For a plane, it will be y equal to m1 x1 plus m2 x2 plus c. For a three-dimensional, for a four-dimensional, it will be three-dimensional hyperplane. It will be like m1 x1 plus m2 x2 plus m3 x3 plus c. So for n-dimensional, it will be like m1 y equal to m1 x1 plus m2 x2 plus etc. up to mn x plus mn xn plus c. So it depends. So various you can use in real world application. SVM can be used for image and object recognition. So you know this optical character recognition and all, or for facial recognition. So you can use SVM. So SVM are very, if the data is in a good pattern and you can separate it linearly, if it is linearly separable, you can separate it. And even I hope many of you use YOLO object detections. So YOLO depends on convolutional neural network, but still, if you have any medical imaging to identify the cancer tumors or growth of some abnormal structures or any outliers. So if some of the cancer data will be, the patients will be in an outlier form. So in order to detect those things, you can use SVM. And even for text and sentiment classifications, so you can project your data set, your textual data to 2D or 3D or 4D or whatever it is. As a human being, I'm repeating it, you can only visualize 2D and 3D, but it does not mean that you can only go for mathematically, you can go for n-dimensional, like it can be 5D or 6D or 100D or any, it depends on data set. So in especially in social media for the sentimental analysis, whether the comments or the paragraphs written by you is a positive word or negative word, so those things you can very easily visualize using SVM. And using the financial markets like stock price prediction, I mean the moment, you can use the SVM to detect the trends or the predict the patterns in the live stocks and all, using the historical financial stock price and all. You can use the data patterns. So this is something like you are detecting some sort of plane or a hyperplane or a line in 2D. So the support vector machines delivers something which will be best separation for a group. So actually we have to find, so if we want to classify something, we need to find a best separable hyperplane. So again, I'm repeating, if it is in 2D means you can separate it with a one-dimensional line. If it is a 3D data means you can separate it with a 2D plane. So think of n-dimensional calculations. If it is an n-dimensional plane which you can't imagine means you can separate it with n-1 dimensional hyperplane. So this is one of the basic mathematical view. So actually you have to find a best optimum line or a plane or a hyperplane which separates the data. So how to find the line? I hope you know the equation y equal to mx plus c. So the y equal to mx plus c means y means it's the x means it's the value in the x axis, and y means it's the value in the y axis. M means the slope and c is the y intercept. So that is with basic mathematics. So in case of a data set, you can think of x as the features. So I hope you know what is a feature. So yesterday in the naive Bayes and as well as logistic regression, we have mentioned what are the features. So what do you mean by a feature in the data set? That is something important. Okay. So I say this, I hope you know what are the features in a data set. Features means you can think of like to predict something, there will be n number of reasons. So if you want to predict, so features are the information we give to the model so it can learn the patterns. So if you want to predict the price of houses, so there are different features, right? So the feature number one will be the size of the house. That will be X1. Feature number two will be the number of bedrooms. So when you are purchasing a flat, you will say whether it is 1 BHK or 2 BHK or 3 BHK or 4 BHK. And then you will check whether the house is how much year of old, whether it is 10 years or 20 years or 5 years. Or if it is near to 1 or 2 years, the price will be very higher. So The features will be like something like size. So something to happen, or if you want to predict some prices, you need the features. So the features only determine the number of dimensions. Okay, so if you have so in the case of a house price prediction, you can think of the size is x1, the first feature. The number of bedrooms is x2, the second feature. The age of the house is the third feature, that is x3. So it's a 4-dimensional data. You need 3-dimension, or sorry, I mean it's a 3-dimensional data. You need 2-dimensional plane to separate these types of data. Okay, so if you're similarly, if you want to say, as yesterday we have given the pass fail data set. If you have the study hours and attendance, you can just check whether your student is passed. So in AI, everything depends on some reasons. So that reason is actually known as uh, the features. So to happen something, you need the features. But how much in we are checking, and the features. Second thing, the features must be independent. So if the features are something like collinear or something, what do you say? It is correlating, means you need to, maybe the data set will be overfit. So it depends what data set you pre-require for each application. So actually, SVM, I said you, right? You need a good hyperplane to separate the data. Okay. So I said you how to draw a line. You can use the y equal to mx plus c. So these things we have done in last class. So to draw a line, you need a x, y points, and you need to predict the slope, best slope. That is y equal to mx plus c. So in machine learning, you can call it as something like weights. So that what is the weight should be given to the features. So like while you're predicting something in the house prediction, even though the size is big, the age of house is more, right? So if you have a very old house and the size of the house is very big, so that you won't get more money, right? You can't sell it for more money. But if the age is, so the age is having more importance. So the slope of the age will be very high, or the weight of, you can say weight of the age of the house will be very high. So you can compare it like that. So in SVM, we generalize the same idea for classifications. So we are predicting some continuous value like house prices, and we want to classify the points into different classes. So suppose you have y equal to mx plus c, you need to predict what is the m, that is the slope, and what is the c, that is the intercept. So if you have multiple features, you need to add those things in the SVMs. So you can together write it as in a matrix form, like omega. So omega, you can think of the slopes or the weights. So mathematically, when you're seeing, you can call it as slope. While you're coming into machine learning, you can compute each features as weight. So x1, x2, x3, etc. will be the features. So what importance you are giving for the for each feature, that is the weights. That means it's literally in basic mathematics or in linear algebraically, you can say it as slope. But in technically in machine learning, we term it as weights or omega or W, whatever you can call it. Or even you can write it as M1 x1 plus M2 x2 plus etc. up to Mn xn plus C. So this is actually determining. But it's the same idea of y equal to mx plus c. So why I'm saying in this term means everyone knows y equal to mx plus c. That's a famous equation to draw a line. So in SVM, actually, we have to maximize the margin. So there are many assumptions in SVM. So you can think of while you're drawing something, or while you're drawing a line in SVM, you need to, every machine learning algorithm works better when certain assumptions are approximately satisfied. So in naive Bayes, we have done each features are uh, independent, right? So each features does not depend on each other. So that was the assumption in naive Bayes. So similarly, we are assuming that the data will be linearly separable. Okay, that you have to assume. So I hope you know what you mean by the linearly separable. So different class should have some distinguishable boundary. If their features are very different, SVM can separate it very easily. And again, you have some extra a technique to reclassify, is to classify them also, you can add an additional term. I will show with a small example in the last equation. Then second thing, the margin between class should exist. A margin actually should be there. So simply saying, if you visualize some data set in a 2D graph or in a 3D graph or in a 4D graph or in a 5D graph, given the condition that you can only visualize 2D and 3D graph in your mind, but in mathematically you can project those things to n dimensional. So that is what is happening. So if you project something in some dimensional, there should be a linearly separable line or a plane or a, what you say, hyperplane. So commonly you can call it as hyperplane. So the assumption is we are maximizing the separation should be maximized, whether it is 1 centimeter or 2 centimeter or 1 kilometer or 1 millimeter or 1 nanometer. The maximum separation, the separation should be very maximum. And it should be robust. The data set must be robustness to the noise. Okay, because the important information lies near the boundary. Because SVM mainly depends on the support vectors. So you can see the vector. This is known as the support vector. So SVM assume these points contain the critical information because that is the starting point. So when you draw a optimum line using the y equal to mx plus c, you can think of y equal to m1 x1 or m2 x2 or anything. Let it be in a matrix form, that is y, capital Y equal to omega capital X. So let it be like that. So you can think of it a matrix form. So these are the support vectors actually. So SVM assume these points contain some critical information since they are very near to the margin. So far away points usually do not affect the boundary much, right? So to predict this point is in class A, or to predict this blue color point is in class B, then it's very easy, right? You can consider this line and you can calculate in which part of the graph or which part of the space these points are happening. But what about this nearest point? If the nearest point should be like something like what you say, closest to the boundary. So those are having some critical information regarding the separation. So features should be very meaningful. So that is what I'm trying to tell. So SVM assumes the input features actually, which helps in the classification. If you have some bad features which reduces the performance, means it's a problem for the SVM. Similarly, like I can say, if you are giving a data set for cancer patient prediction, so you're giving the entire lifestyle and the tumor size and something like some cell shapes of a cancer patient, the tumor size will be very useful, right? It's a useful feature. X1, you can take it as tumor size. Then the tumor cell shape, you can take it as something like what you say. It's also very useful. You can take it as X2. But the patient age. So nowadays, the not only aged person is having cancer. Normally, the person who are like 30, 35, even we can hear that even children is also having cancer nowadays. So the age is not that much a big factor to predict something, right? You can with age you can predict, because even like 50, 60 aged people, those who are having very good lifestyle. So if they are not consuming any alcohol, if they are not consuming any junk foods, if they are eating only very healthy food like vegetable and something like that, so that they're going for the gym, they're going for the walking, morning walk, etc., etc., so they get a very healthy lifestyle. So those features we are not adding here. So then they won't be their health will be very good and they won't have any cancer. So something like important features and unimportant features you have to detect, you have to delete from the data set. So data should be properly scaled. That is one of the most important assumptions we are doing it in SVM. The data set is properly scaled. So since the SVM is actually distance based, so you are calculating the perpendicular direction and the dot product to get the distance based calculation. So if one feature has very huge value, it dominates other. So that's what I said. If you're predicting the salary calculation, age is not a matter, right? Maybe aged person, it's not about, but your experience in the company, or if your experience in the industry will be more, will have more salary. the salary dominates the distance calculation. So we can use the normalizations and standardizations before when we do the SVM. Okay, so that is something like important. You can normalize the data set, or you can standardize the data set. So before training any machine learning models like SVM, we often pre-process the data. That is known as pre-processing. So two important pre-processing techniques are something like normalization. We are normalizing the values. We are scaling the values. You can think of like that. You are scaling it to, so yesterday in logistic regression. So in linear regression, it was you can expect the values will be from minus infinity to plus infinity. Any values you can get. But in logistic regression, from minus infinity to plus infinity, you rescaled the values into the 0 and 1. That is the probabilistic values. So that is you're normalizing something. So you may get a better result. So you can check with those techniques. So I'm not going more depth into the mathematics, but still I'm giving some hints so that you can get very good results. So that is something actually happening even though in the SVM also. It depends how you standardize the data. So what do you mean by standardizing? So how far a value is from the mean? So in standard of standard deviation, that is what is means. Standardization means you're transforming the data so that the mean becomes 0 and standard deviation becomes 1. So why you are doing that is something like if the mean becomes 0 and standard deviation becomes 1 means it is less affected by the outliers commonly used in SVM. So you can use such techniques. So the standardization means it sends the data around zero value. So values may be positive, become negative or positive. So why we are doing this SVM is uses this distance and margins and something like dot products in. So I hope you know what you mean by dot product. So what is actually dot product? So I hope you know these things. I'm assuming that you know the basics of the linear algebra and all. So in mathematics, dot product is an algebraic operation that takes two equal length vectors and returns a single number. So single number means, so it's taking a two vector and returning a single number. So it's a fundamental in linear algebra, especially used for calculating the angles and project the vector and the work. So that's what I said. We in SVM, we may project into different direction. From the two-dimensional, we may project to three-dimensional, or from a five-dimensional data, we can project it into two-dimensional if we are getting a good results. So these combinations you have to try. So, and I hope you know the cos theta, those dot products. So cos theta equal to like something like you're taking the dot product and dividing with the magnitude. So these are something which you perform here in the normal SPMs. So that is happening actually while you deal with the margins. So actually we need to find a better margin to separate the data. So actually, these are the assumptions that I have just noted here. You can, if you are giving to the students and all, you can, these things must be very, so first of all, the data should be linearly separable and the margin should be maximized, and the feature space and dimensionality I have given the explanation. I'm not going more depth into it. So let's actually consider the iris data set. In SVM, if you're doing the iris data set, you can separate it. So you can see for an iris data set, it's very easy to convey SVM. So if you want to practice, give a practice for students, you can give this iris example. So why means in machine learning pattern recognition, the iris data set is one of the most famous beginner data set in the machine learning, because as I said, it contains the sepal length, sepal width, petal length, and petal width. That's features. So the features will be these four things: x1, x2, x3, x4 in a 4-dimensional. And the target class will be the three class names of the flowers. That is, one flower is setosa, second flower is versicolor, third flower is virginica. So that is actually done in the data set. So the problem is that you need to pick which hyperplane. So you can draw a hyperplane like this, you can draw a hyperplane like this, you can draw a hyperplane in any way. You need to perform training and find the best optimum hyperplane. So for the training, you can use analytical method or equation method or something like gradient descent. So there are n number of techniques. So while you do it in Python, you can just, it's very easy. You can just call the function, but what is happening inside the black box of the SVM? So that is actually what we are going to look through. Okay, so basically, altogether, you need to find a best hyperplane which separates the data and maximize the margin of both sides of the data set. So this is how you do the perform. So these things I have just mentioned from line, plane, hyperplane. So if it is a line, means you can separate it like y equal to mx plus c. So in the case of machine learning, we don't say as slope, we say as weight. Similarly, if it is a 3D means you can separate it with two-dimensional hyperplane. I mean, two-dimensional plane. If it is an n feature means you can separate it with this. That's what I was saying it before. So coming to the iris data set. So iris data set is one of the famous data set. I was repeating that one. So using a Python, you can just perform the SVM, but still we can't get the insight. So we'll do a small example in the collab. You can take the collab. So I hope you are ready with the collab. So let me take the collab. We can just perform some basic operations in collab using the iris dataset. So you can visualize the iris dataset. Okay. So similarly, like yesterday we have done, we can import the function. So first let's import the dataset. So you can. So this is to show you how we familiarize with the codes in machine learning. So a sklearn function. So one of the important machine learning Python function, I mean library. So for what we are using that one? So mainly it's an open source machine learning library that supports supervised and unsupervised learning. It also provides various tools for model fitting, then data preprocessing, then model selection, which model you want, then model evaluation, and many other things. So actually the full form of the sklearn is scikit-learn. So it's actually it started by Google. It was a project by one of the scientists in Google. So the name of the project derives its scientific toolkit for the machine learning, originally developed and distributed as a third-party extension to SciPy. So that is what is sklearn. So it's sklearn is one of the important matter in the traditional machine learning items. So let's import a data set. I'm not explaining more. So it's already here. So you can load the iris data. So this is how you import it. So now I think let me import SVM. So to import SVM, you need to write the code from sklearn.svm. You can import the SVM. So it's known as SVC. So I think we can import here. So this is how you run the collab. I think many beginners are also here. So you can learn how to run the code. So you can press this play button. So this is for the beginners. So you can load the iris dataset. I have mentioned what is an iris dataset. So I hope you know what is an iris dataset. So iris dataset is one of the famous dataset. So I'm not repeating because since we have taken it already. So I'm loading the data. Sorry. So I am loading the iris dataset. Load underscore iris. This is the code to load the iris dataset. So actually, I'm not visualizing because yesterday we have visualized the data. So you can visualize it using pandas data frame. Okay, so let's take the features x equal to iris dot data. I'm taking the features. Then I'm taking the output, that is the target, that is known as target, that I'm taking it as iris dot target. So actually this code is actually we need to. So you can see what is the X and what is the Y. You can print and check. Okay, so these are the features. This is the X1, X2, X3, X4. So it's kept in an array in the X. And what is Y? You can see. You can check the Y. So it's the 3 flowers. So you have 3 flowers. One is, what is that? Yeah, Setosa, versicolor, and virginica. So this numbers of flowers will be setosa, then it will be versicolor till here, and then it will be what is that, Virginica. So just I printed and just shown you what is the data set. Okay. So now let's, so we have imported the data set. Now we want to split the data set. We have imported, and you can check the dimension of the data set, but I'm just focusing on the train test for the split. Now we can split the data set into training, and also you can just, so it's a procedure. So no need to split actually. If you want to more data set to train, you can split, but to calculate the performance and measurement, you can just check whether your training is correct or not. You can do it. Okay. So let me split it in the train, X train, then train, then next is for testing. So this is the procedure we have done yesterday also. Don't get confused in this one. So what is the function which is used to train? So that is, we have a function on a train test split. Yes. Yeah, you can split in 80%. So that is given here. Now it is split. So now we can train the SVM in any format. So let me like train the SVM. You can train it SVC, and the function is kernel equal to our function is linear. We have multiple types of SVMs, so we are doing the linear SVM now. So this we are creating a kernel using the SVM model. So the kernel is linear. So I hope you know what you mean by linear. So now you can just train it using model.fit. So this it's the same code. You can train it with X train data and Y train data. So what is X, Y? X means the features and Y means the outputs. So then we train it now. So I think we have errors. So Y model.fit. So I think spelling mistake. X train, Y train. Okay. So I think there is some problem with the data sets. Let me try for the data set splits. Load iris. So this is okay. So let me split the data size. I think that is a spelling mistake. So now let me fit the curve. I think spelling mistake is okay. It's done. So the training is done here. So since it's a very small data, the training will happen very fast. So now you just give a sample. So I said you right. So you can see the X. You can just print out and check what is the X. So you can see these are the features. This is the, I have introduced you what is the iris data set, right? So you have the X1, X2, X3, X4, and Y here. So I'm sorry for that. So here you can see X1 is the sepal length, X2 is the sepal width, X3 is the petal length, and X4 is the petal width. So what is sepals and petals is given here. And we want to predict whether the flower is setosa, or we want to predict whether the flower is versicolor, or we want to predict whether the flower is virginica. So here you need to find out 4-dimensional hyperplane. So you can't think of 4-dimensional. You can think of 2-dimensional, 3-dimensional, 4-dimensional. So you can separate it here actually. You need to find out a separation. So you can give an equation y equal to m1x1 plus y equal to m2x2 plus y equal to m3x3 plus I'm sorry, y equal to m1x1 plus m2x2 plus m3x3 plus m4x4 plus c. Now you need to predict which is the most optimal hyperplane. So that is what is known as training. You can start with the random numbers, and you can come up with the with an optimal hyperplane. So that is known as gradient descent. You have something like analytical solution. You can give direct equations using these values, and you can predict what is M1. I mean, you can calculate what is M1, what is M2, what is M3, what is M4, and then C also. That is a y-intercept. So there is different ways, and you have linear algebra equation to predict. So I have shown you what is the equation to directly calculate the M and C in a slope. So that is actually what is doing in the training side. So here you have the sepal width, sepal length, petal width, petal. Now you have to predict the flowers. So now let me add a sample. So I'm introducing a new data, that is unseen data. We'll predict something like 6.0. So it's a new unseen data. So it should be in a multi-dimensional. So I'm giving it in 2 dimension. Okay. So then you have 3.0, then something like 4.8. Any values you can give, just for testing. Okay. So I don't know, some of you are doing with me. Okay, you can just follow. I'll share the code and the sample. Now you can predict. So the predictions is equal to model dot predict the sample of this thing. You can predict here sample. So just print what is the, you can print and check predictions. So it belongs to the second flower. That is, what is the second flower? It's the Iris virginica. So this is how you predict something in the form of Iris data set. Okay. So you can even print the flower name also. You can just type the code like print. I mean, no need to give that one also. You can just like Iris dot target. You can print what this flower is. Just instead of the names, you can just print out the names. So you can predict the predictions. Okay. So this is how you do the predictions. So the flower name is Virginica. See, it's aligned 2. So each and everything will be converted into vector. I mean, a number. So while you're converting Virginica, it is named as 2. So in the data set, that's what we have seen. Setosa is termed as 0, versicolor is termed as 1, and Virginica is termed as 2. So that while you print the things, you can see, right? While you load the data set, when you type the X, you can see the everything is converted into numbers. Similarly, if you type the Y, that is the target, or the labels or the class names, you can see the flower name 0, then 1, that is something like what is it's known as Setosa, Virginica, versiflower. So these 3 flowers. So that is actually what is coming here. So this is how you predict. Now, if you want to predict the entire test set, you can do those things also. So it doesn't mean that you need to bring some other things. So this is how you predict something. So entirely what we have done is what is actually happening mathematically here. We'll select a few samples row wise from your data set to work with. So you can think we have the entire data set. We are representing 1 or -1 or 1 or 0. Any numbers you can represent 0, 1, 2. So each class represent their own numbers, and then we are predicting a optimal hyperplane. So for a 2-dimensional data, it will be what you say? You need to predict a 1-dimensional line. For a 3-dimensional data, you need to predict a 2-dimensional plane. For a 4-dimensional data, you need to predict a 3-dimensional hyperplane. So it goes on. So for the flower, it is like 1, 2, 3, 4. Okay, 1, 2, 3, 4. So you need to predict a 4-dimensional hyperplane which separates the flowers. So this is actually happening. You're finding a best decision boundary. Okay, so if you want to train means you can start. You have different. So actually, Y X X2 X3 So because Y is the target value or the class labels or class names. X1, X2, X3 are the features. Then what is omega 1 or M1 or M2 or M3, whatever it is? What are the weights and slopes that you need to predict? So you can do it in different ways. You have a gradient descent method. So for that, I need 2 hours to mention what is gradient descent. That is one of the important topic in the machine learning. So you can refer if you want. I'll give you the slide and notes. It's ready with me. So I need an extra 2 or 3 hours to make you know what you mean by gradient. So actually, you are starting with a random number and then you are decreasing with, or you are changing the values and checking which is the best suitable training set for your or which is the best optimal values for the x1, I mean m1, m2, m3, m4, and c. So that is actually you're predicting, and you're predicting a good line. So which is the best one? So how you will know which is the best line? So that we have a loss function in the. I'm just skipping the things because you can refer it. The notes are given; it's very clear. So these things all and all I have told you. So the equation, how you're predicting. So you can see that the hyperplane is actually omega y equal omega x plus c. So in terms of graph, you can think y equal to mx plus c, or y equal to omega x plus b, or whatever it is. So usually in machine learning status, we used to say as weights. In linear algebra status, you can term it as slope. So both are the same only, but technically different. So you can think of this. The optimal hyperplane is omega x plus c equal to 0. Why we are terming it as 0 means it is the starting boundary. So above this, you can classify as +1, and below this, you can classify as -1. So the positive side of the, the positive side of the boundary will be one class, and positive side of the negative side of the graph of the boundary will be minus class. So you can just find out a optimum line, but you need to have certain conditions. So how can we find an optimal line? So you can think that this is omega x plus b equal to 0. So this will be omega x plus b equal to 1. So you can think the next margin. So this is the boundary line, and these are the margin. You have one boundary line and two margins. Why you need that one? So actually that these things are, you can expect mathematically, but in a space this won't be there, right? You can think in a space with n dimensional, many things are scattered around, and you want to classify these things. So mathematically you can say this is a boundary y equal to mx plus c equal to 0. This is mx plus c equal to 1, and this is mx plus c minus 1. So just take the separation, and you will get 2 divided by the magnitude of the vector. So actually you must this is the basics from, I don't know, you are remembering to calculate the distance of a point x from a hyper to the hyperplane. So you want to, so there is a point in plane, and you want to calculate the distance uh, certainly using a formula. So that formula is actually known as the dot product, and then you are taking the magnitude. So I have given what is the things very clearly. You can note it. So you are finding a best margin actually. So that you need to maximize the margin. Maximize the margin means it's 1 by omega, or 2 divided by the omega, or W or M. So you are minimizing. Then maximizing 1 by omega means minimizing. So these things are given in the notes very clearly. If you have any doubt, you can contact me. So with different margin, we are finding the optimal margin, which is very clear. So which is how to know which is the maximized margin means with this equation 1 divided by omega. 1 divided by the magnitude of omega vector. How did you get this? So you just separated here. So this is omega x plus b equal to 0. So this will be omega x plus 1, omega x plus b equal to 1. This will be omega x plus b equal to -1. So you're just separating it, and you get the maximized margin. So how did you take it? It's the distance d from a point x to the hyperplane. So you're just calculating a point from the hyperplane. So this distance will be omega x plus b, and this distance will be omega x plus b. You're separating it to get the maximized margin. Okay, so that I'm skipping how and why and all those things I have given here. I'll share you the slide. You can give it to the students. So the mainly doing SVM is very easy, but you need some labeled data set. Okay. So and the main thing is you need to maximize the margin, or you can say the minimize this vector. So what is that? That is something like slope or weights. So it seeks to minimize the following objectives. So the weight vector that defines the orientation of hyperplane. So weight means something like slope. Slope will be, if it is a single line means it will be only one slope. If it is n dimensional means it will have n vector, right? N elements in the single vector. So it depends. So you can think of like that. So this is how you find the optimal hyperplane. I have given the equation. So let's do one more example with some other data set, so you can know somewhat. So let me take some other examples. So let's take a data set. So let me do it. So we have a make modes data set. So what is it? So let me try to introduce you. It's a data set that is extracted from the sklearn library. So making two interleaving half circles. So you can just search for the make mode. So you have different shapes in that data set actually. So it's drawn by the graph. So just we'll try for the classification. You can check it later. Let me import it. So from sklearn. So I hope you know the codes. Maybe you will be familiarized. So if you have any doubts, you can ask me. Okay. So import make mode. So this it's a data set. Okay. So you need to know what is a make mode. So those things you can refer it later. So there are n number of data sets. So actually a mode data set is not linearly separable. We are trying to check using this data set. So make modes is a function in scikit-learn used to create an artificial non-linear data set for classification. It generally data is shaped like a mode, half circle. So mainly you can, what it learns is it has some features. I will display those things and show you. Okay, so let me import it. So you can know. So you can think I'm taking the X and Y equal to. So I'm taking with it's having its own function, the make moons. So let's take an n samples of 1,000 or something like that. So let me display it for you. So I'm having some errors. So let me import the matplotlib. So whenever you do the matplotlib, you need to import the matplotlib as PLT. So actually, you need to. So this is the code matplotlib dot pyplot. So this is the as PLT. So you can visualize the data. This data set is something like the separation of this data set is something like a half moon, or it's something like a, so that's why it's called. So you can refer this data set, so why it is calling like that and all. So I don't have time to mention that one since we are running out of the time. So next is we are splitting the data. So we have taken the XY from here. So I have taken the X and Y. X means the features and Y means the output or the labels or the class names or whatever it is. So now let me split the data, X train, comma, Y. Okay. I mean, next is X text. So we are splitting the data set, comma, Y train, underscore, Y test. Y test, comma, sorry, Y train, comma, Y test. So it's, so actually we are using the function train test split. Okay, so it's used to split the data set from X and Y for training. So you can split it as test as test splitting size. You can do it 80%. So 80% will be in training side and 80%, 20% will be in testing side. Okay, so that's it done. So this is how you prefer the training and testing things. So this is the function. Sorry, this is the function actually. Well, that's fine. So you can check this. Okay. So now let me train. So there is a function known as RBF to separate the non-linear data. So you can see the data set here, which we imported is a non-linear. You can't separate. It's a non-linear function, right? You can't separate linearly. It's not a linearly separable data. So in SVM, we have something known as RBF. So it's a technique to calculate the non-linear data. I mean, you can train the data. So next is something like model. So actually, you have to use some other models anyway. Model.fit. So you can use the X train and comma Y train. Okay, this is how you do. So now the training is over. Since the data set is very little, we are. So this you can just predict some. You can predict the Y prediction is equal to. You can predict it. So this is how you predict. So you can't understand actually what this data set is. It's not an application data. The data set is only for the study purpose. You can just predict the X text. So you can see the Y predictions. So nothing is there to visualize, but we can see. So see, this is the labels predicted. So now if you want to calculate the accuracy, so for each and every, how much percentage is the correctness we got? So since the data is non-linear, what is the correctness of this training? So we can check the accuracy using accuracy score function. How accurate the data set is. So you can check with the Y test and Y prediction by comparing the results. So I think I'm having an error. So actually name accuracy score is not defined. So I think we need to import some other, okay, function from sklearn dot metrics. So it's a metrics, yeah, import accuracy. Then it will be, yeah. Now you can just print and check what is the value for the accuracy. How much accuracy is our, yeah, we got 80% result. So 24% some wrong happened in the predictions. So actually I'm not diving more depth into it. You can just check each and every values where we got wrong. So what we do, what did we do? So actually a data set, if you get like this, it's non-linear, right? Actually you can project it into an higher dimension. Okay, you can project this type of data into different dimension. So that is what is actually happening in the RPF. So you have respective equation for that one. So what is you are doing it? You are formulating the constraints and then you are separating. You're calculating in P. So next case is when you have some sort of what you say misclassification in the RPF. I mean in the SVM kernel. So what can you do? So we will introduce a slack variable. So that is known as a slack variable. So if some of the data is misclassified, so this is known as soft margin SVM. All points has to be in hard margin SVM. All points had to be in separate, linearly separable. But real world data is messy, right? Sometimes it overlaps. Sometimes noise exists. Sometimes outliers exist. So perfect separation is impossible. That is why we figure it out. So actually some points enter in the wrong side like this. So this also happen. Mistakes can happen. So like you can see here, blue point crossed the margin, orange point cross its margin. So data is not perfectly separable here. So in such case, we introduce a slack. We are adding a value of theta. So it's called slack variables that measure how much a point violates the margin. So this is means the point, if a point is correctly classified outside margin. So you can introduce it if the slack variable is equal to 0, the point is correctly classified. If the point slack variable theta is inside the margin, it's still classified. So real world data, it does not be like something like medical data or human behavior or stock prices or biological signal, may not be something like linearly separable. So at that time, you have SVM has some address to focus it. So small mistakes are okay if generalization improves. So you can add a term theta to neglect a few mistakes are acceptable if boundary becomes more robust. Okay, so that is allowed a small deviation of for smoother safe road. So soft margin SVM allows some points to violate the margin using some slack variables. A term is introduced there. So you are just adding something so that the first term is actually you don't know which term of the data set is crossed. So that also you are introducing it here. So that is known as slack variables in soft margin. So if your data set, if some of your project data set, you can no need to teach it. If any projects you are facing for such assurance, you can, the misclassified point you can address here. So you can see the theta is greater than 1. That a term is added to neglect it. Okay. So here you can see this line is the hyperplane. These are the margins. The dotted lines are the margins. And you can see the support vector. So what is the support vector? It's the first vector which is in the margin. And what is the misclassified point? That is theta is greater than when a term is greater than theta. So you're actually adding to the point. So you're actually adding that term. How much points are misclassified, that you're adding. And you have a C parameter, that is regularized parameter, that is set by the user. So I'll give this. So what you're doing is actually you're projecting, if the data is not linearly separable, you can project it to some other dimension data. So for projection, you need to write, so you can use some quadratic functions or cubic functions or some other functions, which you can get a best result. So here you can see the linear boundary is not possible. But if you're performing the RBF, you can calculate with some other functions. So I think the straight line, you can think it's a linear function. But a curved line, you can just try with some other, what you say, support vectors for different quadratic functions. So you are projecting your 2D data to 3D data, but fakely. So that is what is happening in RBF kernel. So that is something you need to understand. What is the RBF kernel? That's what we have done. So RBF stands for radial basis function. It's most commonly used in SVM. So the main for the data which is non-linear and the straight line cannot separate the class, you can use it. RBF kernel creates the curved decision boundaries. Instead of using the straight hyperplane directly, it transforms the data into higher dimensions so that you get some sort of classifications. So for that, you can use the squared distance between 2 points so that the graph will be something like square graph. So this is something like quadratic graph, right? So like that you can expect. So you can project and check in which graph it is. So like you can think like circle graph or curved graph or complex boundaries also you can draw. So imagine you are having a magnetic influence. So the nearby particles strongly influence each other, right? So this is what is happening. So that is known as something like kernel trick. So for a nonlinear data, you are projecting into higher dimensional. You are mapping the input space to some other feature space so that you get a linearly separable data. So actually in machine learning, kernel function is a way of computing the similarity between two data points in a higher dimensional space. So that you are transforming something into n dimensional. So here you can think like quadratic graph, the square graph. So you are projecting x1, x2 features to some squared graph that is known as kernel function in the polynomials. So with different, so SVM means actually not only linear, you can have the quadratic function, you can have a cubic function that is something like this, you can have a reciprocal function. So wherever you can separate a two-dimensional data, you can project it into n-dimensional and check whether you can try. So these are done for the research purpose and very heavily industrial purpose. So normally you can teach for students the normal basic SVM. So that's it for today. So I'm running out of the time. So today's session is just 1 hour. So for today we'll stop here, and for to take next topic we'll try from tomorrow or the next day, which what I'm having allocated. So for today that's it from my side. So I hope I have conveyed from my side. That's it for today. Thank you and have a nice day. This is Yaser signing off.
Thank you, sir. Thank you for sharing your time with us. Participants can leave the meeting now. Thank you all. You can leave after filling the feedback form. Feedback link is shared in the chat box.